So in the previous lecture, as we have studied about the comparison of FET with BJT, and we have also discussed the various types of FET, which are JFET and IGFET, or you can say that MOSFET. So today we will start discussing junction field effect transistor, first type of field effect transistor, in detail. So what is this junction field effect transistor? It is basically a three-terminal device having three terminals. One terminal is source, second terminal is drain, and third terminal is gate. So it is a three-terminal semiconductor device. This whole bar, it is made up of a semiconductor, either N-type or P-type. So a junction field effect transistor, it is basically a three-terminal device, semiconductor device, in which there will be conduction of the current. And we know that in case of semiconductors, we have two types of charge carriers, electrons or holes. But here, this FET, as we have already discussed in our previous lecture, that this is unipolar device. Unipolar device means mainly the current will only be due to the motion of only one type of charge carriers. Those are majority carriers. So if this semiconductor bar, if it is of N-type, then we know that in N-type semiconductor, the majority carriers are electrons. So in this semiconductor bar, the current will be conducted because of electrons. But if in case this semiconductor bar, it is made up of P-type material, then this channel, it will be P channel instead of N. And we know that in P channel or in P-type semiconductor, the majority carriers are holes. So at that time, the current between the source and drain, it will be conducted by holes. And this whole semiconductor bar, it is made up of uniformly doped material. The doping is uniform throughout the cross-sectional area of this bar. Means the N-type doping, this is N-type semiconductor bar. It means N-type dopant is doped inside this intrinsic semiconductor bar, and the amount of doping is same over the whole area of this semiconductor bar. It means it is uniformly doped semiconductor bar and having ohmic contacts at both ends. Ohmic contacts are actually metal semiconductor contacts, metal semiconductor junctions. For the electrical contacts, we apply some layer of metal on this side and some layer of metal on this side. So metal semiconductor junction will be formed on this side as well on this side, and which are known as ohmic contacts. So it is a uniformly doped semiconductor bar having ohmic contacts at both sides or both ends, from where we have two terminals. On one side we have source, on the other side we have drain. And as you can see, on both sides of this bar, we have a P-type material. And because of the diffusion of this P-type material on both sides of this N-type semiconductor bar, so we will have PN junction. So there will be semiconductor junctions, or you can say that PN junctions on this side as well as on the lower side of this semiconductor bar. So this is a uniformly doped semiconductor bar having ohmic contacts at both ends to form two terminals, source and drain, and having semiconductor junctions on both sides of the bar to form the third terminal, which is common terminal, which is known as gate. And here we have the pictorial representation of n-channel JFET. So for the construction of n-channel JFET, we need n-type bar. So we have n-type semiconductor bar. That is why this FET, this JFET, it is known as n-channel JFET. And in this n-channel JFET, here we have a PN junction. This is P-type, and here we have below this n-channel, n-type bar. So here we will have one PN junction, and on the lower side, again we have P-type material diffused over this semiconductor bar. So again we will have a PN junction on the lower side as well. So this is the PN junction which is formed at the opposite sides of the bar. How? By doping the bar with the impurity of the opposite type than that of the bar. If this bar, if it is n-channel or if it is n-type, then the impurity with which you will dope here, it will be p-type. And if you have this p-type bar, in case of this p-channel FET, then the impurity with which you will dope here, it will be n-type. So in n-channel bar or in n-channel FET, gate is p-type, and in p-channel FET, gate is n-type. So here we have p-channel junction field effect transistor, where we have taken the p-type semiconductor bar having uniformly doped p-type semiconductor bar with metal semiconductor junctions, or you can say that ohmic contacts at both the ends to form two terminals, source and drain, and to form the third terminal gate, we have doped the opposite sides of the semiconductor bar with the impurity of the opposite type than that of the bar. So here the bar is p-type, so that is why the impurity which is diffused over here, that is of opposite type, that is n-type. So this n-type impurity, it will make this portion n-type, and this common terminal, it is known as gate. And what is this ohmic contact at both ends? These ohmic contacts are the electrical contacts or metal semiconductor contacts or the junctions, where the carriers, they are free to flow into the semiconductor and out of the semiconductor, and there is minimum resistance across the metal semiconductor contact. So here we have a structure of n-channel JFET. This is n-type semiconductor bar or n-type channel of JFET, and these two are this portion and this portion. This is metallic, so this is metal semiconductor junction, and this is also a metal semiconductor junction. So these both ends are ohmic contacts. And on one side we have a source terminal, and on the other side we have a drain terminal. Source will supply the carriers and drain will drain out the carriers. And the current in this JFET, it will be because of the flow of the carriers from source to drain. Either electrons in case of n-type channel FET or holes in case of p-type channel FET. And as this n-type channel FET, in this case gate will be of p-type, so this is p-type gate. And why they have written down p plus here? It means the gate regions or the gate terminals, they are heavily doped. The amount of dopant is very high in this portion. So this positive sign means the amount of doping is high. And if here we will have negative sign, it means the amount of doping is low. And if there is no negative or positive sign, it means the amount of doping is normal. So this means our gate terminal, it is heavily doped. Now what about the biasing? Here we have this P and this N. On this side we have semiconductor junction, or you can say that PN junction, and on this side as well we have one PN junction. And if there is PN junction, then there you will also have a depletion layer. So there will be some depletion layer in between this PN junction and in between this PN junction. And actually this portion, this whole portion, it is a depletion layer. But the width of the depletion layer, it is not same across the length of the bar. Why is it so? I'll explain it later. First, just remember that if we have a PN junction here and a PN junction here, between the P-type gate and N-type channel, we have two PN junctions. And if we have two PN junctions, then there will also be a depletion layer here as well as here. And when we haven't applied any biasing across this gate or across these PN junctions, when we have not applied any external voltage across these two PN junctions, as we haven't applied yet any voltage. So at that time, the width of depletion layer between this PN junction and across this PN junction, it will remain same throughout its length. But as soon as we apply external voltage here, the width of the depletion layer across these two PN junctions, it will change along the length of the bar. Why? We'll check it in our next article. So here just remember that the task of this drain, it is to collect or drain out the charge carriers. And it will only be drain out or collect the charge carriers if it carries opposite potential to that of the channel. As we have N-type channel here, so the current will basically, because of the electrons, and these electrons, they will be collected by the positive potential. They will be attracted by the positive potential. So that is why in N-type channel JFET, drain is always made at higher potential or positive potential than that of source, because the task of this drain is to drain out the charge carriers, and here the charge carriers are electrons in N-type channel. And if the charge carriers are electrons, they will be, as they carry negative charge, so they will be attracted by the positive charge, or you can say the positive potential. So that is why this drain terminal, it is made at higher potential or positive potential than this source terminal. So, and the voltage potential is known as VDD. So drain, it is at higher potential, that is positive potential, than the source. Then what about the biasing to these two PN junctions? These two PN junctions, they are always reverse biased. These two PN junctions, they are always reverse biased. It means the gate terminal is always reverse biased. Here our gate is P-type. It means it will be connected to negative terminal of the biasing voltage. only then it will be a reverse biased junction. And then the source, it will be connected to the positive terminal of the external voltage or the biasing voltage. So in this way, in N-channel JFET, what you have to remember is that whether it is N-channel FET or it is P-channel FET, you will always have to reverse bias the gate terminal. In case of N-channel FET, gate will be P-type, and if gate is P-type, then its biasing voltage will be negative. Only then these two PN junctions, they will be reverse biased. And in case of P-channel FET, our gate will be of N-type, and if our gate terminal is N-type, then to reverse bias this N-type gate, we need positive voltage. At that time, in P-channel FET, as our gate terminal is negative N-type, at that time it will be connected to positive terminal of the biasing voltage. Only then it will be a reverse biased. And the current entering from the source side, it is known as source current. The current entering from drain side, it is known as drain current. And the current entering from gate side, it is known as gate current, that is IG. So this is all in this lecture. And in the next lecture, we will discuss about the operation of FET. And in that lecture, we will discuss that why the width of this depletion layer, it is not same, or why it changes across the length of this semiconductor bar.